Hello, this is Electricity and Magnetism, Part 8. Today I'm going to talk about direct current circuits, resistors in series and parallel, and RC circuits with resistors and capacitors. So let's talk about DC circuits in general. We already saw in the previous chapter the basic notions of EMF and internal resistance of a battery. So we take those batteries and connect to loads, which are resistors, and we have our basic circuit, right? So name these points A and B. So we're talking about a potential difference across the terminals, VAB, which will result in a current if we connect a load of R. So the current goes from the positive terminal to the negative terminal of the battery. In this case, a clockwise current. So according to Ohm's law, the terminal voltage will be equal to potential drop across the resistor, IR. Okay, a very basic circuit, the most elementary form, a complete circuit. Let's talk about different ways of connecting these loads, the resistors, to our battery. So let's say we have two of these. This is what we call a series connection. We kind of talked about this in the previous chapter when we discussed internal resistance. Internal resistance of the battery was in series with the actual resistor, the load, right? So let's repeat that idea. So this is delta V AB. And our current now goes through both resistors and the battery as well. Okay, so like if you could write down the potential drops and increases, and they should all add up to 0 if you end up with the same point you start. Let's say you start point A and travel along the current. You first have R1, and the potential drops when you go through R1. By what amount? Exactly equal to R1 times I. Now you're here, going from the left-hand side to the right-hand side of the resistor. The potential drops again by this amount, R2 times I. Now we're at point B, and you go through the battery, potential increases, right? So the first one was negative R1I, the potential dropped, and the second drop is equal to R2 times I, and these will be compensated, if you will, by the battery there, and you will get back to the point you start. So there will be no change in the potential. You start at A and end up at A. Okay, so I could rewrite this as R1 plus R2 times I, and that will be equal to delta VAB, just rearranging the terms. And according to Ohm's law, this should be a resistance. And this is what we're going to call the equivalent resistance. Okay, so if I could claim that these two diagrams are equal to each other, I'm taking the two resistors out and replacing it with the same, with another resistor, which would give me the same current. That's the idea behind equivalent resistance. Okay, replace R1 and R2, the combination of R1 and R2, or as many as you like, many resistors connected. You take that combination and replace it with a single resistor, which is called REQ, R equivalent. Okay, so that in the end you would get the same current. If you connect an ammeter somewhere here, you would read the same number. Okay, so this is what we call a series connection. And a series combination of resistors, you simply add them up. R equivalent would be R1 plus R2 plus R3, etc. Okay, so the rule for a series is there should be only one way for the current. Okay, there is no branching, no bifurcation. Right? So there's only one way for the current, and you simply add them up, you get the net or equivalent resistance. It's like taking a piece of wire, it has a resistance, right? Example, I mean, the simplest thing you can imagine. A long wire. Now, if you remember, the resistance of this is given by the resistivity times the length divided by the cross-sectional area. But what if you divide this now into smaller parts? You cut it up. Each segment will have, a resistance, Ri. Let's say this segment here has a resistance Ri. I stands for a number between 1 and, 100. Depends on how many pieces you want. But you add them up. So Ri, a summation over I, from 1 to a large number, doesn't matter what number is, you end up with the original wire, that is R, right? Of course, this logic holds only if A is not changing along the length of the wire. So that's a series. What if they are connected in parallel? Okay, now you are familiar with these types of connections from capacitors, series and parallel. What about a parallel connection like this? Okay, let's name these R1 and R2. Is it possible to find a representation for these two and call it the new R or REQ, just like this one? How am I going to find it mathematically in terms of R1 and R2, right? That's the idea. So this is the positive terminal of the battery on the left-hand side. See, there's nothing in between this terminal and the resistors, right? I mean, the wire itself in practice would have some resistance, but let's ignore that. So this point here is the same as that point, which is this point, which is also that point. These are all the same point. Similarly, on the right-hand side, the same thing. Which means that if you have a voltmeter, you can connect that voltmeter in parallel with your battery. You would read a number, right? That number would be exactly the same number if you connect the voltmeter over here or over there. Same. So voltages are the same. That is the thing about parallel connection. So what changes then? Remember what I said about branching off? That's what happens. The current that goes through the battery is not the current that would go through R1 or R2. So this current that goes through the battery and goes up here, I. Now when it comes to this point here, it has to split into two. So one part of the current would go up. And that will go through the first resistor. That's why I call it I1. Okay? So if you take I1 out of I, what is left? I minus I1, right? So the current that goes through the second resistor is whatever is left from the original current, which is I minus I1. If you will, call it I2. Doesn't matter. It's a different current. I2. So that current goes through R2 and then follows the wire and then comes here. And the I1 meets I2 over here. What do? They combine. Think of two rivers meeting and forming a larger river before they reach the sea, right? So here I will have then this current, which is equal to I1 plus I2, and that was I minus I1. What is left? The original. So they add up to give the original current I, and that goes inside the battery, goes on and on like that, okay? So in a parallel connection, voltages are the same, but you add the currents, whereas in a series connection, you add the voltages. Now check it out. In the series connection here, R1 times I was nothing but the potential drop across this. So if you connect a voltmeter, this is what you would measure. R1 times I. Similarly, here you would measure delta V2, if you will. So delta V1 plus delta V2, this plus, that would give you the terminal voltage. Okay, so in a series connection, there's only one current, but you add the voltages. But in a parallel connection, there's only one voltage for both, but the current splits. So you add the currents. All right, so here's how you add them. I is equal to I1 plus I2. Now, the total current, if I want to write it in terms of delta V, I need to divide delta V by this combination, which I called REQ. So that REQ times that current would be equal to delta V, right? What about I1? Take the voltage across R1 divided by R1, that's I1. So the second current is similarly equal to delta V divided by R2. Get to those delta V's, so what do you get? 1 over REQ is equal to 1 over R1 plus 1 over R2. And then you solve for the equivalent resistance, right? You will get R1 times R2 divided by R1 plus R2. So what if you have more than two, they're all connected in parallel, then you have to apply the formula same way. 1 over R1 plus 1 over R2 plus 1 over R3, dot, 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 okay? So that's the parallel formula. You always end up with a resistance less than the individual resistances of the resistors you're using in a case of parallel. Specifically, if you have two 10 ohm resistors, you put them together in a parallel, you get a 5 ohm resistor if they're parallel. Two 10s, 1 over 10 plus 1 over 10, 2 over 10, therefore 5. If you put them in series, 10 plus 10, 20. Okay? So if the resistors you use are all the same, let's say you use 40 ohm resistors, you have 4 of them, they're all in parallel, divide 40 by 4, you get 10 ohms. If you line them up, 40 plus 40 plus 40 plus 40, right? 160 ohm resistor. So that works like that. And then you may have a combination. You may have a combination. Very simple example. Let's say this is 9 ohms. Sorry, it's not a capacitor. I don't know why I did that. Resistor. 9 ohms. And then you have here 2 ohms. And then you have 2 ohms. And these are connected to a battery. I don't know, 10 volts. Very simple. Find I, which is the current that goes through the 9 ohm resistor, and then find I1. And I2. Let's say this is the I2. Okay, so when you solve a problem like this, it obviously has both parallel and series connection, okay? So you gotta decide which ones you want to start with. So you don't start with 9 ohm and then 2 ohm and see if these two are in series or parallel. You don't, because there's 2 ohm in the middle, right? There's a branching off. So whatever your group you're isolating from the rest, it should be really simple, okay? You should be able to tell if it is parallel or series without any ambiguity there, okay? So you don't do 9 and 2 first. Instead, you take this one, these two 2 ohm resistors, because they're obviously in parallel. Call it R prime. Okay, you have two 2 ohm resistors, so R prime will be only 1 ohm. 1 over R prime is equal to 1 divided by 2 plus 1 divided by 2. That is 1. Therefore, R1, R prime is 1 ohm. Just half of it. Now, consider R prime and then 9 ohms. They are obviously in series, right? So this is equivalent to 9 ohm resistor, and this R prime, which is 1 ohm. Same circuit, I only have 2 resistors. What do I do when I have 2 resistors in series? I add them. So 9 plus 1, 10 ohms. Okay, this is I. So I will be equal to 10 volts divided by 10 ohms, 1 amp. Okay, so I found this. That's 1 amp. What do I do now? I come to this point here where the current splits. Now, in this problem, since both branches carry the same resistances, they're both 2 ohms, the current exactly splits into half. So 0.5 amp from one side, 0.5 amp from the other. So I1 and I2 are both equal to 0.5 amps. What if they were not the same? What would you do then? All right, so what if you had something like this? I'm not going to use numbers now. I'm going to keep it more generic. R1, R2, and R1 is not equal to R2. Okay, so what would I do? I would do exactly the same, meaning find the big current here by considering these two as parallel, so R prime would be R1 times R2 divided by R1 plus R2. Therefore, the equivalent resistance would be R plus that, and then find I by dividing the potential by that number, everything the same. But to find the current through each resistor, I would need the potential drop from left to right here. So I would need this potential difference. What would this voltmeter measure? Okay, so that's the idea. So that's, let's call it V12, or V12 is not a good, because VAB, let's call it AB, VAB, delta VAB. So this delta VAB would obviously be less than delta V. Why? Because there's the other resistor there that helps decreasing the voltage there. So I'm going to take delta V, but subtract the drop I times R from it. Okay? Now that is delta VAB, and that is equal to R1 times I1. That's also equal to R2 times I2. So this is I1 here, and this is I2. Okay? So I would find delta VAB by subtracting IR from delta V, and then divide that by R1 to get I1. And to get I2, either subtract I1 from I, or just divide delta VAB again by R2 and get I2. Okay, that's what I would do if these two were not equal. But this problem had both of them 2 ohms, so I would say, okay, half of the current goes that way, the other half goes through the other resistor. All right, so that's the series and parallel in a nutshell. And most of the time, you know, you should be able to solve complex combinations, you know, maybe involving 5, 6, 7, up to, you know, God knows how many resistors. You should be able to analyze them part by part, start with a part that is identifiable and then move on like that. But in some problems, it may not be easy. The one very famous case is where you have 5 resistors. Okay, example. What if you have something like this? How do you do this one? Now the difficulty is you can't find any pair here which are easily, you know, found to be parallel or series. Like if you take any pair, like you may say, okay, what about these two? Are they in parallel? Well, from this corner, they look like they're parallel. Yeah, they're branching off, but the other sides don't meet because there's a third one here. That messes it up, right? So are they in parallel or in series? Actually, you don't think like that. You can't find the answer by looking like that. So what do you do then? There are different methods. But to do that, we have to understand, or we have to learn the Kirchhoff's rules, okay? So, Kirchhoff. I'm sure I spelled it wrong, but Kirchhoff's rules. There are 2 of these. The first one you're already familiar, okay? If you complete the cycle, which means that if you when you travel in a circuit and you end up with the same point you started, you complete the loop, right? The potential drop, whether it's drop or increase, doesn't matter. It has to be 0. So The first rule is you add those changes in potential. They should add up to 0 if a loop. Okay, so you go in any loop. It's, as long as you come back to the same point, it is a loop. And you add the changes in potential, they should add up to 0. That's rule number 1. Rule number 2 is at a junction like this, there's no current, there's no way the current will escape in air, right? So everything has to stay in those wires. So the leaving currents leaving the junction, should add up to give the original current. So if I'm having a current here, I, which splits into two, I1 and I2, let's say, okay? Then the in current is I, and the out current is I1 and I2. The left and right hand sides should match. Same idea about when currents meet. So let's say it's I1, I2, and then you have these two currents here, I3 and I4, just names, okay? So I3 and I4 are the in currents. They should add up to give the out current, which is I. Going in, out. Okay, sometimes it's this equation is simply written in terms of a summation like we had. So I, an index here, I, maybe, little I, 0. But then you have to accept the convention. If am I going to take the positives as in and negatives as out? Yeah, sure. Or take negatives as in, positive out. Doesn't matter. But if you add them up, you get 0. It's just this equation written differently, okay? So using this idea, you can solve this problem. And I'm going to show it in a little bit, but let's do some simple examples first, like standard examples of application of Kirchhoff's rules. Let's say I have a battery here, 9 volts, a resistor, 10 ohms, another resistor here, 12 ohms, and then I have a battery here, another resistor, let's say 12 volts and 5 ohms. Okay, so given the resistances and the battery, the terminal voltages of the batteries, find the current through each resistor. Okay, so here's what I'm going to do. I'm going to assume directions for these currents. If I'm wrong in my assumption, I will end up with negative numbers. I can always fix them, so no big deal, okay? So meaning this, there will be a current here through the 10 ohm resistor, which I'm going to call I1. So this is I1 is the current that goes down here, I1. But here I have a junction, so now I have to change the letters, okay? So maybe there's a new current now, which I'm going to call it I2. Similarly here, I3 is what goes through this resistor, and it enters junction from above. The first junction. The second junction over here. I2 enters that junction and splits into I1 and I3. Okay, fair enough. So this will be I2. So let's apply Kirchhoff's rules. Now, I already know what happens at the junction, right? That's rule number B, or second number 2. I1 plus I3 is I2. They add up to give me I2. Similarly, I2 splits into I1 and I3. So that's 1. Okay, I have 3 unknowns, right? If I have 3 unknowns, I'll need 3 equations, independent equations. So the other 2 equations that I will need will come from the loops that I was mentioning. So loop, okay? So take a loop. Let's say, how about this? I take this clockwise loop here. That's my number 1 loop. 1. I'm going to start at a point on that loop. Doesn't matter where it is, as long as it's in the upper square there. Let's say I start here. I move to the right. I travel in this direction. Go through 9 volt, and then 10 ohms, and then go down. There's nothing here. Go back to the loop, or follow the second current. Go through the 12 ohm, and then go up and end up the same point. What will happen? The potential changes will be added to give me 0. Okay, that's the idea. That's Kirchhoff's rule. So that will be my second equation. So going from the negative terminal of the battery to the positive terminal, there was obviously an increase in the potential. By what amount? By 9 volts. 9 volts. But when I go through the 10 ohm resistor, the potential will be dropped. It'll drop because I'm traveling in the same direction as the current. Remember, current flow is from, not current flow, charge flow, or current, direction of current is from high potential to lower potential. So minus 10 ohms times that current, I1. All right? Now I'm here. Go down, move left. Now when I'm going over the 12 ohm resistor, same thing happens. The potential drops by 12 ohms times the current, which I called I2. And I'm back at the same point, so it is equal to 0. Okay. This is the second equation. And then the third equation. Why don't I pick another loop here? Let's say this is my second loop. Clockwise, counterclockwise, doesn't matter, okay? Just pick something and then stick with it. Stick to it and then don't change it along the way, you'll be fine. So let's say I start here, the lower right corner. Now moving to the left, I'm going against the current, all right? The 5 ohm resistor I'm talking about. I'm going against the current, so potential increases. By what amount? By this amount, 5 ohms times I3. And then I go from the positive terminal to the negative terminal. I'm talking about 12 volt battery here. So there's a decrease in the potential by 12 volts. Now I'm here, go up, there's nothing. Now I have to go through the 12 ohm resistor. Again, I'm going against the current, so the potential increases. 12 ohms times I2 again. So 1, 2, 3 equations. Just solve them, okay? Just solve them for I1, I2, and I3. I'm not going to do it here, but I think it's straightforward. So going back to that example, the difficult one. Let's try to do that. Okay, so you can't solve this by separating the resistors into series and parallel. It doesn't work because of that middle. They call this a bridge, you know, the Whetstone bridge. So let's say this is 12 volts, 1 ohm, 2 ohms, 3 ohms, I'm just picking arbitrary, 4 ohms and 5 ohms. So question again, what is the current? Right? What is the current that goes through the battery? What is the current through each resistor? They're all different. So here's what we do. We're going to name currents here. Let's call this guy I. So we have I here. Now some of this I goes through the 1 ohm resistor. Actually, since 1 ohm is less than 2 ohms, that part will be greater than the other one. Okay, so you can say it would be, you can divide I by 3, and 2/3 would go from I1, 1 ohm, and the other third from 2. But I mean, those are just because I picked those numbers like that. So in general, it could be anything. I'm just going to call I1 now. That's why I'm I1. So this will be I minus I1. All right. So what about 3 here? This current I1 will be splitting into 2 again. I'm going to call this I2. And this will be then I1 minus I2, using same logic. Okay, I'm just applying Kirchhoff's second rule directly. When I come to this junction, I have I minus I1 and I2 coming together to form the current that goes, the current. The current doesn't go, okay? I keep using that way. The current is, the charges go, okay? Just a figure of speech. So I minus I1 plus I2. All right? So this is just to avoid too many numbers. If I pick a number, an index for each resistor, I would end up with 5 I's and then the big I. There's no need for that, okay? Just apply the Kirchhoff rule directly, so you would end up with only 3 unknowns, I1, I2, that's all. So here, at this junction, what happens? I minus I2 plus I minus I1 plus I2. If you add them up, I2's cancel, I1's cancel, and what is left is again I. Just 3 variables are enough. 3 unknowns are enough. So once you get this, apply the other Kirchhoff rule, meaning pick 3, I guess. You gotta pick 3 of them. Loops, and then write down the equations and solve them. That's all, okay? So let me do one of them, and then you'll do the other one yourself. So let's pick this one here. A loop like this, meaning 12 volts, and then minus 2 times I minus I1, because I'm traveling in the direction of the current, minus 5 times, what is it? I minus I1 plus I2 equals 0, etc. Okay, find 2 more equations and then you'll be done with 3 equations and 3 unknowns. So that's how you solve this specific problem. It's not very easy, not as easy as the previous one, or maybe it is, I don't know, depends on, I mean, you can just punch these numbers in a calculator. The calculators will do it for you, okay? Simultaneously solving a system of linear algebraic equations. No big deal, but you gotta be able to write the equations correctly, okay? So let's review the rules again. Rule number 1, battery. If you're traveling from left to right, delta V is a positive number. If you're traveling from right to left, delta will be a negative number. Negative. Positive. Simple as that. When you're traveling through a resistor, see, the thing is, once you decide what the direction should be, you don't change it. It's okay if it is wrong. In the end, you will find a negative number. You know that you did wrong. Just make it positive. But once you pick a direction, just stick to it, okay? Don't change it. So if the travel is from left to right, this means you're parallel. with the current, then the drop, potential drops. If you're moving in the opposite direction, if you're traveling against the flow, against the current, potential increases. If you just keep those in mind, you should be fine, okay? So those are Kirchhoff's rules, series and parallel connections. Let me stop this video, and in part 9, I'm going to talk about RC circuits. All right? So bye for now. Let me stop the recording.